Hello and welcome to lecture 28 of Math 2R03. In our last lecture, actually, it was our midterm, but the lecture before that, we introduced inner product spaces. And kind of the goal for today's lecture is to continue to develop the properties of inner products. So in the very first part here, I'll just quickly review the definitions and the results that we need, and then we'll jump into the main results today where we're going to learn about orthogonal decomposition, the Cauchy-Schwarz inequality, and we'll apply some of these results to some classical results in geometry. So here I will just quickly review everything here about what an inner product space is. It's a space that has what's called an inner product. That means a function that associates a pair of elements in your vector space with another element in the field F, whether that's the real or complex numbers. And this function has the property that when you do apply the inner product to U in itself, you get a number strictly greater than or equal to, or a number greater than or equal to 0. It equals 0 if and only if the vector u is 0. We have an additive property in the first spot, so this is equal to uv wv. We are able to pull out scalars out of the first spot, and we have the property that when you take the reverse direction, so you look at the inner product of v and u, you actually get the complex conjugate. Okay, and we also introduce what the norm of a vector is. That's defined to be the square root of the inner product of v with itself. And we define what it means for two vectors to be orthogonal. That means that the inner product of those two vectors is 0. And we actually proved that in an inner product space, we have what would be called a Pythagorean theorem, which says that if your two vectors u and v are orthogonal, then they satisfy the relationship that u plus v squared is equal to u squared plus v squared. And we also have the following fact that will be useful in today's lecture is when you scale a vector by a complex number, or a complex number or a real number, the norm of that vector is the same thing as the absolute value of your complex number times the norm of v. Okay, and so just remember that this is a complex number. So if lambda is equal to b plus I, the norm of that, or the length of that vector, is the square root of a squared plus b squared. So we need kind of all of these results and definitions for today's lecture. And the first new thing that we want to talk about in the part 1 here is about orthogonal decomposition. So orthogonal decomposition is something that you would have seen in Math 1B03, but let me just kind of give you the initial setup. So what you're doing is you're fixing a vector v, and then given any vector u, you want to write u as in the form as u is equal to u1 plus u2. And you want to have the property that u1 is a multiple of the fixed vector v, and then u2 is orthogonal to the vector v. Okay, and so this is the picture you might be familiar with in Math 1B03. So, and it's a picture of R2, but it's going to kind of guide us to trying to generalize what we did in first year linear algebra. So you're fixing a vector v, and the dotted blue line is the set of all multiples of v. Okay, so now I'm going to go and just take an arbitrary vector u. So here's my arbitrary vector u, and I want to break u up into something that is a multiple of v and something orthogonal to v. So that means I want some vector on this line, and I want some other vector that's orthogonal to it. Okay, so I'll do that in green. What we're looking for is this would be the vector u1. Oh, I didn't draw it to scale, so let me fix it in a second. And this would be my vector u2. Okay, so let me fix that up. Right, so here I have that. So u is equal to u1 plus u2. And I guess I'm writing them as vectors, so let's just kind of use that notation. So this is exactly what the original question is asking, is we want to write u as something that's a multiple of v, so it's on this line, plus something that's orthogonal, so that means that it's perpendicular. And in Math 1B03, the notation that we used was that u1 is the projection of the vector u onto the line spanned by v. Okay, so you might have seen the notation slightly different, but that's kind of what we were doing, right? So u1 kind of projects down onto this onto the space spanned by the vector v. So this is what we want to kind of generalize, okay, this orthogonal decomposition. And as I said, although the picture is in R2, it actually works in any inner product space. So you can fix a vector v, and given any vector u, you can write it as a multiple of the first vector plus something that's orthogonal to that vector. So we'll pause here, and then we'll give a proof of that particular statement in the next part.